Right, we've dealt with proton NMR spectra to this point, and we've dealt with aspects of chemical shift, of the integration, and of the splitting, and how we interpret these three aspects in exploring proton NMR spectra. But I'd like to now move on to carbon-13 spectra, and just to make you aware that carbon-13 is less sensitive because carbon-13 has a lower gyromagnetic ratio than the proton, and also carbon-13 is only 1% of all carbon that's found naturally. Remember that carbon-12 has spin 0 and so cannot be observed in an NMR spectrometer. A final point is just please be aware you can't integrate carbon spectra, but it doesn't really matter because we can normally see where signals are. We can normally see the carbons giving rise to signals. We can count them. Right, so here's an example of a carbon-13 spectrum. First of all, look for the solvent. Many solvents contain carbon. You'll see that several solvents don't contain protons, so we don't have such an issue in proton NMR spectra. But almost all solvents contain carbon, and so you need to look for the carbon signal. So if it's chloroform, the carbon signal will be at about 77 ppm. Please don't use this in your analysis of compounds. It's simply a solvent to get the compound into the spectrometer. Okay. Right, so here is the carbon-13 NMR spectrum of ethyl acetate, and it's interesting to note that we've got 4 carbons in our compound, and we see correspondingly 4 signals in the NMR spectrum. Again, in the notes that are available to you in the handbook and the workbook that I've placed on RE Connected, there are chemical shift tables, and so you can use chemical shift tables to identify and assign every carbon in the molecule to a signal in the spectrum. So, for example, at close to 200 ppm, we have the carbonyl-carbon. At around 60 ppm, we have the CH2 that's near an oxygen, and of course the other ones can be assigned on their relative positions to other chemical functionality. So, use chemical shift tables to assign particular carbon centers to signals in the spectrum. Carbon-13 spectrum often come with another source of information. There are other experiments that I will not go into detail with, like the attached proton test and the DEPT 135 experiment. These provide information on the number of hydrogens, the number of protons that are attached to a particular carbon. So these can pick up whether a carbon is quaternary or if it's a CH or CH2 or CH3. And so I'm transferring that information to all the carbon spectra that we have available in this course. And what I want you to look for are these designations of multiplicity, the S, which would mean that it's a quaternary carbon, a T, that means it's a CH2, a Q, it's a CH3, or a D, which would be a CH. So that information also helps to assign signals to compounds. So for example, I know from the chemical shift that there is the carbonyl is going to be over here, but I know from the multiplicity information it's the carbonyl because it's the only carbon with no hydrogens attached, and so it should be designated as a singlet. Similarly, the CH2 is going to appear as a triplet, and so I can quickly identify that CH2 in the NMR spectrum from its multiplicity. Okay, please be careful. So here we go. I've designated so the CH2 and the CH3s are easily identified from the multiplicity information. Okay. Please be careful with some compounds because you might have carbons that have some chemical equivalence. So the first thing you need to do when coming to a carbon spectrum is you need to just check that the number of signals matches the number of carbons. So in this compound, I hope you see that there are 5 carbon atoms, but in the spectrum there are only 4 signals. The question is, how do we deal with that? Well, of course there is some chemical equivalence, and so within the isopropyl group you'll notice that these 2 methyl groups are identical to each other, and if they're chemically equivalent, if identical, the signal will appear at exactly the same point in the NMR spectrum. A clue that will enable you to match such cases is normally where there's doubling up of a carbon signal, the signal's more intense. So have a look at this spectrum. Can you see that the most intense intense signal is this one over here? So therefore both of those CH3s are giving rise to that signal over there. So the most intense signal is overlap of the 2 identical groups, and just see the other CH3 is close but not quite overlapping. The CH near an oxygen is de-shielded somewhat, between 60 and 70, and the carbonyl is there. But look out for the multiplicity information, and look out for doubling of signals in the carbon-13 spectrum. Have a look at this case. Of course, once you've assigned the solvent in the signal and the spectra, you've only got 4 signals for a molecule that has got 1, 2, 3, 4, 5, 6 carbons. So the question is, why are there only 4 signals when there are 6 carbon atoms? And the answer is that we have doubling up. This molecule is symmetrical, and so this carbon is identical to this carbon, and this carbon is identical to this carbon. But of course the quaternaries are different to everything. So the quaternaries are going to appear on their own, but of course the CHs, these carbons, are going to double up. So the most intense signals are from the overlap. So we know that we've got a CH and a CH and a CH and a CH. And of course the less intense are where we have a single carbon giving rise to that signal.